Alright guys, so for this video we're going to be talking about our 4 important reactions for this next exam, which are SN1, SN2, E1, and E2. And before we start going into what like characteristics and the properties of each one of these reactions, let's talk about some general terms. So some general things that we have that are important for these reactions are what we call nucleophiles. I know she like brings it up in class, and it's kind of like, whoa, what the heck is a nucleophile? We have electrophiles, and we have leaving groups. So we have 3 important terms for this unit, okay? And something that, just to write down what they are, right? So nucleophiles are molecules or atom with excess electron density. So it's electron rich, right? Has plenty of lone pairs to use to form bonds, also known as attacking. Okay, so I just wrote this very general term right here. So what I wrote was nucleophiles are molecules or atoms with excess electron density. They are electron rich, right? And they have plenty of lone pairs to use to form bonds, aka attacking, right? The process of forming a bond is what we call attack. So nucleophilic attack, right, is the process of that nucleophile forming a bond with the electrophile usually, okay? So it always has to be electrophile. An electrophile, molecule, atom with electron deficiency lacks right, and these are susceptible. I have no idea how to spell that. Susceptible to attack. Okay. All right. Cool. So, electrophiles are molecules or atoms with electron deficiency. They lack the right amount of electrons, so they don't have octet sometimes, or they the way they have either a sigma bond instead of a lone pair that makes them either positive, or they're connected to something that is pulling their electrons away that makes them partially positive. Things like that are electrophiles. So they are not, they don't have the right amount of electron density. Okay, and then leaving groups are usually, they are groups that are either becoming, they are groups that are electronegative, and they are pulling on a sigma bond. Okay, so I'm not going to write this out, but some examples of leaving groups are, let's say I have this chlorine, right? This chlorine is very electronegative, and what it's doing is it's not allowing the equal sharing of the sigma bond between this carbon and itself. It's pulling on this the sigma bond, and it's hogging those electrons to itself. So what this does, it creates electrophile, right? And it makes itself a leaving group, right? So what it does, it's pulling electron density this direction, and it's making this carbon partially positive and making itself partially negative. Okay, so partially positive, partially negative. So this sign just means partially negative, partially positive. Okay, so that's what's happening here. And this can also be the same whenever I have things like, right, if I have water, right, this is, dehydration, so this water is partially positive, right, because this oxygen has too many bonds. So it's really pulling on these electrons in the sigma bond, and making this a very partially positive site and this a partially negative site. Even though it's positive here, it's pulling these electrons toward itself. Okay, so it's making this a partially positive site. Not really that much partially negative over here, but it's wanting to make this bond into a lone pair that it can own. Right? It wants to own these electrons. This one wants to own these electrons because of their electronegativity, and this one specifically also because it has a positive charge on it. So these are leaving groups. Okay, so what they do is they, given the opportunity, they leave and they create positive charges, right? So this carbocation is a electrophile, right? And this is susceptible to be attacked by a nucleophile. Okay, there's some general stuff that looking at before we start talking about start looking at the exact reactions. So I just want to talk about halogens for a second, and some things about halogens, right? I'm just gonna take something from the book right here. So one thing about halogens, okay? Oops. I'm gonna cover this up. All right. So one thing about halogens that makes them good leaving groups is we're going to look at their electronegativities, right? So we have I, Br, Cl, fluorine, so this is increasing electronegativity, fluorine with the most. Then we have bond length, right? So the length between, usually it's a carbon that we're looking at, and that halogen, so fluorine, chlorine, bromine. As we get to the heavier atoms, bond length increases. And then we look at the dipole moment. So dipole moment is a combination of both these physical properties. Okay, so this is going to give us, the actual dipole moment that controls how good a leaving group is. So the bigger the dipole moment, the better the leaving group, right? So the more I am creating, separation of partially positive and partially negative, that's a dipole moment, the better my leaving group is, right? The more eager it will take those electrons away. So I have chlorine is a better leaving group than fluorine, even though fluorine is more electronegative than chlorine. And this is because the slight difference in this difference in bond length. So this has a longer bond length, so this overcomes fluorine's electronegativity. It makes chlorine a much better leaving group than fluorine. And then fluorine is better than bromine, right? And then iodine is worse than all of them. Okay, so this is very important. Write this down and memorize these orderings, okay? And one other leaving group that's also very good that I want everyone to know is something called OTOS. OTOS is just a leaving group. It's a very big leaving group. It's we never write out what it actually looks like. We just write it out like this. So attached to a molecule, it would be written like this. And just know that this is a very good leaving group, and it's very readily leaves. Okay, so it's just as good or better than chlorine. Okay, I think it would be better. Just look at that was something you have to see on exams with how she prioritizes it, and we'll talk about why it's important to know what's better and what's worse. So moving on. All right, so now let's start talking about reactions. So the first reaction that I want to discuss is the SN2 reaction. Okay. And for SN2, right, some important things about it. Okay, SN2, I'm just going to write out some facts. So the leaving leaving group, carbon, okay, it prefers to be on a primary, okay, over secondary, over tertiary. And actually above this primary is a methyl group attached to X. So X just represents a halogen. Okay, I know this, like, what the heck am I writing? But some things that we need to know, and I'll give examples and I'll explain what these mean. So leaving group carbon likes to be in that order, right? We need a strong nucleophile needed, okay? And we need solvent must be aprotic. Aprotic helps the reaction progress, okay? And the rate of the reaction is equal to the reaction constant, K, and then we have the nucleophile. So this is the nucleophile strength times the substrate. So how good the substrate is. The substrate is the thing that has a leaving group on it. Okay, so this is very important. All right. And then I'm going to write out some SN1 details over here. Okay. So leaving group, carbon, likes to be tertiary, above secondary, above primary. Right. So writing these things out, but essentially for SN2, these are the only things that work. If you have a tertiary leaving group, and you're thinking, is this SN2? This will never happen, okay? And this is even, kind of iffy right here. So it's really primary and methyl, right? And mainly primary that you see the most. And then for SN1, we really just see these two, right? Not this and not this, okay? So this will make sense as I give more examples, but for now, right? And weak nucleophile can be used, okay? And solvent must be Aprotic, helps. The rate is equal to K, and it's only dependent on the substrate, right? So we have these things, okay? So what do these things mean? So the first thing, leaving group carbon. The leaving group carbon is essentially, right? So primary, secondary, tertiary. Degree of the carbon. So let's say I have this carbon group, this carbon chain, and then I have a chlorine here, okay? First thing that I have to do to understand this is to characterize the degree of this carbon. So the degree of the carbon is described by how many other carbons it's attached to. So this carbon is directly attached to this carbon over here and this carbon over here. So this would be a secondary carbon, okay? If I have something like this, chlorine is attached right here. This carbon is attached to one other carbon, right? So this would be primary. And then if I had something like this, okay, this carbon, so always look at the carbon that has a leaving group on it. So this carbon right here is attached to 1, 2, 3. So this would be tertiary, okay? So these are 3 different types of centers, okay? And the reason for this is because there's different steric effects and different stability effects that each one of these provides. So for SN1 is looking at a stability, right? It's looking at forming a stable intermediate. So I'm put INTMDT, right? It's looking at forming a stable intermediate. And all these things help form a stable intermediate. So this helps form a stable intermediate, and this helps form a stable intermediate. And we'll talk about why this happened, why this is different than SN2. And this means a first order nucleophilic substitution, okay? And this is second order nucleophilic substitution, okay? So both of these are nucleophilic substitution. The difference is just the order between them. So this first, this is second, right? So the second order, first order. And SN2 is a one-step reaction, and SN1 is a two-step reaction, okay? And I hope everyone has memorized this stuff so far. There's more things to know. Okay, so next thing we need to talk about is the nucleophile strength. So we need to talk about what that is, all right? So moving on, if we're looking at nucleophile strengths, right? So we need to characterize some molecules that are potentially nucleophiles and that we can use. So I'm just going to copy something from the book, a very helpful table, in my opinion. So I have this. So let's take a look. So we have some common nucleophiles listed in decreasing order of nucleophilicity and hydroxylic solvents such as water and alcohols. Right. So just really quickly, I also need to talk about protic and aprotic. So these are protic solvents right now. Right. Water and alcohol are protic solvents. So looking at these molecules, these are some. This is what we want to look at: the strong nucleophiles. So ignore these other things. Okay. So what I'm looking at is these things right here. So they're just giving us some strengths, right? Increasing strengths, and I want everyone to. I think there's an order. I mean, this is the order of strengths, but the ones that she commonly uses, these are all good nucleophiles right here. The ones that she commonly uses are what I call shrink, so SH, SR, I, and CN, right? So NC. So shrink, right? Shrink. So what this is S minus, SR minus, I minus, and CN minus, right? So the minus is over here. So these are all good nucleophiles that she commonly uses, and you also have things like nitrogen, and you have phosphorus, and you have OH and OR. You also have OR. So essentially, the common trait between all of these is that you have excess electron density. So all of these have excess electron density. You have these extra pair of lone pairs that actually makes these molecules negative. All of them are negative here, right? Besides this nitrogen right here. This one is not negative, and neither is this one. Okay, but these are the main ones that she'll be using always. So just if everyone's confused about the R just is a general way of saying any carbon chain. So this could mean CH3, could mean CH2, CH3. It doesn't matter. It's just a very general way of saying I have some number of carbons. Okay, so that's all that means. So these are our common strong nucleophiles, and I need these things to have an SN2 reaction. So these are needed for SN2, right? So SN2 requires these, and if anything that's not these, they're automatically moderate or weak. Okay, so anything that's not among these and really these, she doesn't really use these a lot. So she doesn't really use this, and she doesn't really use this, and she doesn't really use this, and she doesn't really use this. This is used, right? Anything that's not among these is not a strong nucleophile. Okay, it's automatically a weak nucleophile. Right, and a nucleophile, the requirement to be any type of nucleophile, amongst all of these, the similarity is that they all have at least one lone pair. So there's at least one lone pair, and a lone pair is needed to form a bond. So that's what a nucleophile is. It forms a bond with the respective electrophile. Okay, so that's what that is. So now that we've talked about that, let's talk about protic and aprotic. Protic is, let's say aprotic, and then we have protic. Okay, and so what this is, what does this sound like? Protic, proton. It sounds like proton. So it's the lack of a available protons. So and this is available protons. So it's indicating partially positive hydrogens, right? That are used to help stabilize the solvent or to not let it be stable. So aprotic is used in SN2. And the one thing I want everyone to think about in SN2, SN2 needs strong nucleophiles. It wants a primary carbon, okay? So SN2 wants things that, so SN2 wants something like this. It wants one of these, and it wants an aprotic solvent, okay? And this is all because SN2 is a very fast reaction, okay? SN2 is fast, all right? And SN2 wants to happen as quickly as possible. And it's a one-step reaction, and I'll show the reaction in a little bit. And so all these things help this reaction happen quickly. So primary doesn't have any steric hindrance, right? And it doesn't form a very stable carbocation. So this happens very quickly. Something comes and attacks here, and this happens very quickly. It's a one-step reaction. Aprotic, so when we have the nucleophile, an aprotic solvent is a solvent that won't stabilize this negative charge on the nucleophile. And aprotic essentially means that I have things that are like ethanol. So I have, ethane, right? Ethane or methane or just carbon chains. I'm doing this in a liquid environment that's not stabilizing these negative charges at all. These non-polar molecules are not helping stabilize it. So some examples of aprotic solvents are DMSO and acetone. She uses these a lot. Okay, so these are aprotic. Protic, on the other hand, are things like water, right? Alcohols, so ethanol, methanol, propanol, all those things. And what those things have, so let's look at water, right? Water looks like this. Water has partially positive hydrogens, right? And these can do hydrogen bonding, right? And what these will do for the SN1 reaction, because SN1 likes protic. And what it'll do, SN1 forms the carbocation, right? And what this will do, the O minus, partially positive, will associate with this charge over here and help it stabilize. So this will help stabilize these charges. And then nucleophile, right, it's weak, and I guess the hydrogens will also stabilize with those, okay? But it's mainly that these help stabilize the carbocation, right? I want everyone to think about SN1 as a reaction where I'm trying to make the carbocation that forms the electrophile as stable as possible, because essentially we want it to exist, we want it to form. And that's what SN1 is. And I'm talking without showing the reaction, but I want SN1, I want the carbocation to form. I want the leaving group to leave. Okay? So let's talk about what I mean about these things. So for SN2, a general reaction would be, let's say I have this right here and I have a chlorine, okay? And let's say I have, for example, I have SH minus. This is one of my strong nucleophiles. And there's the arrow, okay? Whatever, she does this on an arrow. Let me just put it on the arrow. So this will be the general setup. She'll have this, and she'll have an arrow, and she'll have like SH, right? And then she'll have, let's say, DMSO and negative charge. And what happens is this lone pair from the nucleophile comes and it attacks the carbon that the leaving group is on. So I said this is my leaving group, my halogen, and this is going to cause this to leave. So what happens is I now have SH attached to the molecule plus the chlorine, right? And so what DMSO is, it doesn't stabilize this nucleophile. It keeps it, keeps it as reactive as it was. It keeps it as unstable as it was. Nucleophiles are unstable. They have negative charges. They have excess electron density. They want to form a bond. And then for SN1, we have the opposite. So what happens in SN1, so everyone see how this is a one-step reaction. This comes and attacks and this leaves. So SN1, let's say I have this tertiary carbon with the chlorine. And what happens in the first step is this leaves. And the reason this can leave is because this center is stable enough once it leaves to hold a positive charge, right? So the positive charge here. And if I want everyone to remember from the previous test that for carbons that have positive charges or carbons that have radicals on it, in order of stability, we have them preferring tertiary over secondary over primary. Okay, so whenever, this is why SN1 works on tertiary and secondary, is because the leaving group leaves and it can form a tertiary carbocation or a secondary carbocation, which are relatively stable compared to an SN2. We have primary and secondary and these don't leave right away. So it's a one-step reaction. The nucleophile helps this to leave. And over here, this is leaves on its own because it can just take these electrons from the sigma bond and just leave and form this carbocation. And so this is what's forming. And this is why we want to have protic solvents, right? The protic solvent will help stabilize this partially positive, this actual positive charge with its partially negative charges, my bad. Okay? So the protic solvent will help this be stable. And I want this to be stable because I want this to form. If this is stable, more stable when it forms, I have the bigger chance of this forming, right? And so I want this to form so that my weak nucleophile, which does not help promote the reaction, promote this to leave, right? So an example of a weak nucleophile is anything that has a lone pair and it just, you know, it's not negative. It doesn't have to be negative, and it just come and attack. So an example of this is water. Okay, water has two lone pairs, right? And it's not negative; it's neutral, but it has a lone pair, and these are partially negative. Okay, so they're weak. They're weakly nucleophilic. So what happens is this can come and attack, and we'll go into some extra details about these reactions in a little bit. So water will come and it will bond to the site where it had the partially positive charge, and I form this, right? And I form a positive charge on the water. And the thing that you guys need to know about SN1 reactions is that usually, almost always, whenever you have something that's neutral and it forms an extra bond, it becomes positive. And what we have to do, we have to deprotonate this to make it neutral. So we take another water and we deprotonate this. And I get this as my answer, my product. All right, so this is my product. This is my product. All right, so this is my product, and now I just want to get into some examples now to show you guys how these reactions work. All right, so first the page, and take this. Okay, so this is so the first thing I always have to do. This is the general setup for how all your reactions are going to look like on the exam. Just going to give you a molecule, right? It's going to have a leaving group on it. It may not have a leaving group. I don't know. That might be a trick question. But the prerequisite has to have a leaving group, and then she's going to give you things on an arrow. And you have to look at what you're given and determine, do I have SN1, do I have SN2, do I have E2, do I have E1? And I'll talk about E2 and E1 in a second. So this is my leaving group, right? My halogen. So I've discovered my leaving group. And now I need to characterize the degree of the carbon. So this carbon right here is attached to 1 carbon, 2 carbon. So this is a secondary carbon, okay? All right, so I have a secondary carbon. I have a good leaving group, right? This is one extra detail I forgot to mention in the previous slide, is that my leaving group has to be good, right? So SN2, it always has to be good. It always needs to be a good leaving group, okay? SN2 wants to happen quickly, so I need to have, you know, a chlorine is better than a fluorine, it's better than a bromine. You need to have good leaving groups on your molecule so that it can progress quickly. And then I need to have a good nucleophile. So I need to, where's my strong nucleophile? Stronger, good nucleophile. So she's given me these two molecules right here. One of them is a solvent. I mean, they're both in the solvent. And then the other one is going to be acting as the nucleophile. So I have OCH3 minus and I have CH3OH. So this one has excess electron density. It's negative. This is my nucleophile. And what's going to happen is this is going to come and it's going to attack from the back side. Okay? SN2. So this is the details that I wanted to talk about. SN2 does backside attack. Okay? Alright? And what this means is that flips the stereochemistry once it attacks. So sometimes stereochemistry might not be indicated, and at that point, you know, it doesn't matter, right? The previous example I didn't indicate any stereochemistry, but here it's indicated very clearly. So when I draw this, what it's going to do is SN2, the nucleophile is going to attack from the back, and it's going to cause this stereochemistry to flip, okay? And that's going to flip it from R to S or S to R, okay? So when I draw this, I don't need to know if it's S to R, or I don't need to know what it was before, right? But I'm just going to draw this as I normally would, okay? And the leaving group is going to be replaced by the nucleophile, okay? So this is the substitution, nucleophilic substitution. So before, the leaving group was on a dark wedge, and I said it's going to flip. So that means the nucleophile is going to be present on the light wedge. So I have this OCH3, and then over here I have my CH3 group. Okay, so the CH3 group moved from the light wedge to the dark wedge. All right, so this would be my answer. All right. Okay. All right, so now let's look at an SN1 type of reaction. So for SN1, let's see, right, it'll typically look something like this. Okay, so what we have here, we need to first find our leaving group. So our leaving group is a chlorine, and then I need to find what the degree of this carbon is. So this carbon is attached to 2 other carbons. This is a secondary carbon right here, right? And you'll notice that there's 2 boxes, and there's a reason for that. SN1 can attack from the top and bottom, okay? And so SN1 can attack from both the top and the bottom, and what that means is once we form our carbocation, so we said this is an SN1, I have a weak nucleophile, I have heat helps promote a reaction, right? SN1 is slow, so heat helps promote it, make it go faster, and the leaving group leaves, okay? So what we have is this carbon with a positive charge, right? I have another carbon over here, and I have this CH2, CH3 group, okay? All right, and what happens in SN1 is that the nucleophile, I'll draw this out first, with its lone pair, it can either attack from the top, from the bottom of this molecule, or it can attack from the top of this molecule. So it's only when she indicates stereochemistry that you can do this. And what happens essentially, you have one of these groups is just, you have this hydrogen that's just sticking out like this. So I can attack from the top or bottom, and this will affect whether I get, you know, a retention, what we call a retention product, retention or inversion, okay? In SN2, we saw that it flips the stereochemistry, and SN2 is what we have 100% inversion, okay? And inversion. And then SN1 has a mix of both retention and inversion, and it's 50% of each, okay? And this 50% of retention and inversion are essentially going to 50% of it's going to be R, 50% of it is going to be S, and this is what produces what we call a racemic mixture, okay? So SN1 produces racemic mixtures. So this is going to attack from the top and the bottom. So one of these products is going to be it forming the retention. So I'll draw the retention product. So we have this C, right? The retention is going to keep the same stereochemistry as before, right? Retaining. So I'm just going to draw CH3, right? And then I have this, and then over here, I'm going to have my O, this O, OCH3. And notice how I drew it without this hydrogen. This hydrogen gets deprotonated, remember. So initially it would look like this with a positive charge, and then I would use the same molecule, the same CH3OH, to come and deprotonate this, right? This would just come and remove this hydrogen, and this electrons would go right onto the oxygen. Okay? So this is one of the answers. The other answer looks like this. So I'm going to have the hydrogen like this. Actually, my bad. Let's be consistent. All right, keep them in the same position. So I'm going to have the CH3 over here, and then I'm going to have the hydrogen over here, and then I'm going to have the OCH3, and then I'm going to have this, right? So this is an example SN1 products, all right? Now I want to take a second to kind of talk about number one. I actually did number one wrong, all right? And I guess this is it was a good example, right? But there's a reason why it's wrong. So we're gonna look at this nucleophile right here, right? It can act as a nucleophile, but it will only act as a strong nucleophile in a certain situation, and that certain situation is primary. Okay, so I want everyone to pay attention to what I'm doing right here. So the reason why this is wrong is that a strong base, so this is a strong base, OCH3 is one of the strong bases that we're gonna look at. It can only act as a strong nucleophile and perform SN2 only when this is a primary carbon. So I have a secondary carbon, and this will not be SN2, right? So this is it was just an example of how SN2 works, but this is not the right answer, right? Some of it, I think, some of the product will be this, but the major product, the product that we want to write in the box will actually be an E2 product, okay? And now let's talk about E2 and E1. So E2 means elimination, right? E means elimination. This is just second order elimination. And then E1 is first order elimination. Okay? So, right. Now let's list some factors what is required for E2. E2 and both E2 and E1, right, prefer to their leaving group to be on a tertiary over a secondary, way over primary. Okay? And this is the same thing, so tertiary over secondary over primary. And E2 requires a strong base. All right? So what are some strong bases? Some strong bases are OR minus, right? OH minus, right? Any nitrogen, so like NH2 for example, NH2 minus, right? And then we have something called acetylide anion, which is like you have the R chain and you have a C, it's a triple bond C, and at the end of it we have this lone pair, and this is minus. So these are just some examples of some strong bases, right? And we can further characterize these bases, which is important, as either bulky or non-bulky. So a bulky base, for example, is if I had a T-butyl and I have this O minus. So this would be a type of OR, right? This would be a type of this. This is an R group, but it's bulky. These T-butyl group are very bulky. So this would be bulky. I know I'm kind of just skipping around a little bit and talking about different things, but just bear with me. This is a bulky OR group. And another type of bulky that you'll experience is something that looks like this. I believe this is called pyrimidine. So the nitrogen, like this, is a bulky base. Okay, so we need to always characterize our bases as either bulky or non-bulky. It's very important for E2 and E1 reactions. E2. And this is essentially all you need to know for E2. So it needs to be on a tertiary or secondary, and it needs to be a strong base. And E1 is the same thing, except it happens with weak bases. Okay, and here we don't really care about these things so much because we don't no longer have. So if it's not among these, then it's a weak base, right? So usually an example of this is like H2O or ROH. Essentially the protonated versions of these things. They still have lone pairs. They can still be bases per se, but they're not strong bases. So any one of these just protonated minus this one. So NH3, H2O, ROH, that's what those weak bases look like usually. And two rules that we have to look at for E2 is what we call 1,2, it's really big, trans diaxial, okay, position, right? Okay. So it needs to be 1,2 trans diaxial, or it needs to be anti-coplanar. All right. So that's just two rules that we have to follow. So these need to be followed in 1,2 trans diaxial or anti-coplanar. The same thing, just depends on what they're on. We'll look at some examples of this, and essentially this is referring to whenever we have stereochemistry, that the orientation of the leaving group and the hydrogen that the base is going to remove. So let's look at how these mechanisms work. All right. So I hope everyone has this written down and everything. So let's look at how these work, and we're going to look at an example. All right. So if we look at an example, let's see. All right. Let's look at the one that we just did. Okay. Now, the one that we just did is this one, right? We said this is SN1, right? Now, why am I saying it's E1, right? So this is E1. I'm just going to say it's E1 for them already. So one thing you need to know, whenever we do SN1, we can also do E1 because they share very similar properties. So both SN1 and E1, SN1 uses a weak nucleophile, E1 uses a weak base. CH3OH is both a weak nucleophile and a weak base. So you'll have both answers, and the actual question, what it looks like this. All right. So this is not, looks like this actually. Ugh. This is what the actual question looks like. It has 4 boxes, 2 boxes for the 2 SN1 products and 2 boxes for 2 E1 products, okay? So we're just going to learn how E1 and E2 work through example. So what we have, I'm going to draw this out as a regular carbon chain. So we have 1, 2, 3, 4 carbons. So 1, 2, 3, 4. And on the second one, I have a chlorine, okay? Here, the stereochemistry doesn't really matter, right? For E2, we're not dealing with E1, we're not really dealing with stereochemistry. All right, what I'm dealing with is we're looking at where we have available hydrogen, right? Because we're using bases now. And what we're doing in E1 and E2 is we're eliminating a hydrogen, right? We're taking a hydrogen away from an adjacent carbon. These are all our adjacent carbons. So we have 2 adjacent carbons to the carbon that has a leaving group on it. And what it does is it takes away that hydrogen and it forms a double bond, and then the leaving group leaves. So since this is E1 and it works like SN1, first thing that happens is the leaving group leaves, right? So I form this positive charge. Now I'm going to look at my adjacent carbons, and I'm going to look at the hydrogens that are on them. So both of these adjacent carbons have hydrogens on them, okay? And what I'm deciding now is, here it doesn't matter because you write both of them, but what I'm deciding right now is which ones do I take to use with the weak base. So I have CH3OH, and what it's going to do is it's going to take away one of these hydrogens, and these electrons are going to be used to form a double bond to stabilize this positive charge. So let's say I take the right side. So this is going to come, right? And it's going to take that, and this is going to form a double bond right there, and we're going to get this product right here, okay? I'm going to get this, right? And if I take the other side, right? So let's say I have a hydrogen over here. Let's say I took the other side. What this will do, positive charge over there, this is going to form a double bond right there. So I have two different products. So I have this one and I have this one, and I'll just put one of them in one of the boxes, okay? And what we're gonna see with this is what we're gonna see with E2 especially is one of these is more stable than the other, right? So one of them has a double bond that's attached to one carbon group, right? And one of them is a double bond that's attached to two carbon groups, right? So two carbon groups. And the way it works for double bonds is the more carbon groups that I have coming off of a double bond, the more stable that double bond is. Okay? So let's look at these two I just drew. This one has 4 carbon groups on it, so this is a tetra sub. So I call it sub. They're subbed. So substitutions with carbons on it. So this double bond is substituted with 4 carbon groups. This one is substituted with 3 carbon groups. So tetra versus tri. The tetra is more stable than the tri. So this double bond is more stable than this double bond right here. Okay. So if I were to write out which one's the major or more stable one, this one would be the more stable one, and this would be the least stable, less stable. Okay. So there's that. Right, so we have these two products, and then obviously you have the SN1 products up here that we did previously. So that's essentially how it works. Okay, so let's look at an E2 example. So an E2 example, right, let's look at this right over here, and she's gonna have something that looks like this, right? So I have my halogen, right? I have my leaving group, right? Bromine. It's on a secondary carbon, okay? And it's on a secondary carbon, and I have an OR, right? This is a strong base, right? And is it bulky or is it non-bulky? It's not bulky, okay? And I'll show a counter example in a second. Let me just actually put the counter example up that we're gonna do to demonstrate the importance of bulkiness. Come on. Right? Alright, so this one we have a non-bulky OR group, and what's going to happen is I have a strong base, right? And I have a secondary leaving group, a secondary carbon that has a leaving group on it, so this is good for E2, right? This is E2. So E2 requires these two things, and what E2 does is I have two products, right? So I have two products because adjacent to this carbon right here, I have a hydrogen over here on this adjacent carbon, and I have a hydrogen over here on this adjacent carbon. And one of them is going to form a double bond that's more stable than the other, and that's going to give us our major product. So this OR group can come, and it's going to come, and it's going to take this hydrogen right here, and this is going to form a double bond, and as it forms a double bond, it's going to leaving group is going to leave. So it looks very similar to SN2, except that I'm forming a double bond and I'm not substituting this group onto the molecule. So both E2 and SN2 are one-step reactions, and both SN1 and E1 are two-step reactions, and that's why they usually happen together. But SN2 and E2 do not happen together. They have very different conditions, right? So SN1 and E1 happen together. They have the same conditions, right? Same things are used. And so you get a mix of both types of products. And E2, you only get E2 products. SN2, you only get SN2 products. So if I do this and I form this double bond right there, okay, I'm going to have this product first. It looks really ugly what I drew. Okay. Okay. Alright, so I get this one. And if I take this hydrogen away and I form this double bond and this leaves, right, I will get this one. Whoa. I'll get this product. So we can see on this this double bond right here, I have one group, two groups, three groups, right? So this is a tri-sub double bond. It's more stable. And this one right here is a mono-sub, right? I only have one carbon group coming off of this. This is mono. So obviously mono is less stable than tri. So this is what I would get, okay? But this all changes once I have a bulky base. So here, this is the tibutoxide, right? This is what we call it, tibutoxide. It's a bulky base. And what the bulky base does, it flips all these rules on its head. bulky base is not gonna, just like SN2, E2 likes to be a very fast reaction. And because I have a bulky base, this is gonna have a lot more steric interactions with the molecule itself, and that's gonna prevent what we normally would have, a deprotonation of the more substituted hydrogen, right? This hydrogen is on a more substituted carbon, forming the more substituted double bond. So because this is bulky, this is going to come and actually form the major product with the least substituted hydrogen, right? So the bulky base is always going to take the least substituted hydrogen as the major product. And that's because it's less steric hindrance, and it would be much faster for that to occur there, right? So this is going to have a faster rate of production than the more substituted hydrogen right here. So that's the difference between bulky and non-bulky bases. So bulky bases will form the least substituted double bond, and non-bulky bases will form the most substituted double bond. So it's opposite, right? Does everybody see that? So now the mono is here as the major, and this is over here as the minor. And that's just because it's bulky, right? So that's E2 and E1, okay? Now let's look at the E2 transdiaxial and, right, transdiaxial and our anti-coplanar rules. So I'm going to show both, and I'm going to do a couple examples. So these are considered whenever she draws your molecule either as a Newman projection or like with the stereochemistry here, or whenever it's on a ring. So all those things have stereochemistry. Rings have stereochemistry. These have stereochemistry, obviously indicated. So that's when you would consider the anti-coplanar or 1,2 transdiaxial rule. So this is one of our bulky bases, NH2 minus. And what this is going to do, it's going to take this hydrogen. This is going to come over here, form a double bond, and kick this off. So this is E2, right? So this one is it's a basic just introduction to how this looks. And what this is already set up in our anti-coplanar form, and this is why I'm using this one. So anti-coplanar is when you have your hydrogen that's being taken and your leaving group on opposite, I guess this is like the stick on opposite sides. So this is anti-coplanar. So in the same plane, but they're anti to each other. So this setup allows us to have a very much faster reaction, and this is important because it's gonna control the orientation around our double bond. So if I had a different setup, like a different twist, right? Because this molecule, these are twisting, right? These are turning constantly in 3D space. It's always turning. So we're just pausing it at the moment where it has this anti-coplanar format, and we're going to make this what we use to draw our product. And this is important because this tells me, let's say I had R prime over here, let's say I had R, let's say I had O, and let's say I had R prime, okay? This is important because the way, when I find the anti-coplanar format of this molecule, this is gonna be important in identifying how my groups are around the double bond. So I'm going to have the dashes on the same side. So I have R prime over here on the same side, and I have R prime here on the same side, okay? And then I have R, so the wedges on the same side, okay? So this is going to give me the cis product, right? Cis, because both R primes are on the same side. So this is important because maybe I would have drawn this differently. I didn't have the hydrogen, the fluorine, opposite to each other, or I didn't draw it in the right way, and I might have gone the trans product where the R prime is down here and the R is up here. So this is why this is relevant. It's going to show us whether we get a cis or trans product, or the orientation, the one that's going to be the correct answer. And that's why this is important to write out. So let's look at another one. Okay, so this one's not as easy, not as straightforward. Right, so we have this. I have a strong base, right? This is the acetylide anion, right? The C triple bond C negative charge. So this is going to be E2, right? I have my leaving group right here. It's on a 1, 2. So this is a secondary. This works for E2, secondary. All right. So I have that. And what I need to do now is I need to get my leaving group and the hydrogen, right? And I want everyone to remember, for E2, we're looking to form the most substituted double bond. So I could form many different double bonds here, right? Because I have many different adjacent carbons that have hydrogens on them. So I can form a double bond right here. I can form a double bond right here. You know, I can form 2 possible ones. But I'm going to only draw the major one, right? And that's going to be forming it right here because it's the most substituted. Okay? You can look at that on your own. But the double bond, we're looking at this hydrogen to be removed and this bromine right here that's leaving and forming a double bond in the middle. So I need to look at the anti-coplanar format, and this is not an anti-coplanar right now. So I need to get this anti-coplanar, I need to get my bromine into this stick position and my hydrogen in this stick position. So that means I need to rotate this bromine up and bring all these groups, you know, rotate it that way. And I need to bring this hydrogen down and rotate all these groups this way, right? So the way that we're going to do this is, so draw your thing out like this and just put your wedges and dashes, okay? So draw this. Looks really ugly, I understand. And now we just need to rotate our groups in the right way. So I said I'm rotating my bromine up. So that means the bromine is becoming a stick, right? And this CH3 is becoming, right, the dash, right? And then this hydrogen is becoming the wedge, right? And the bromine is over here. All right? And then for this one, I'm bringing my hydrogen down here. This is where I want my hydrogen. The CH3 is going up and it's becoming this right here. And then my CH2, CH3 is going on the wedge. And I hope everyone sees why this is important, because it's going to give you a different orientation of groups on the double bond. So I could just have said, yeah, I know it's a double bond right here and just drawn it, but you may not have drawn it correctly. So now that we do this, you're going to have the reaction. This is going to come. It's going to take this hydrogen, right? And this is going to form the double bond, and this is going to leave. And so I have the CH3 and this CH3 on the same side, right? Okay. And then I have the hydrogen. And then I have the CH2, CH3 on the same side. So CH2, CH3. And what I get is I get these as cis, right? So this product is different than having this up. And so you always have the cis and trans. So you may have drawn, we need the cis here. That's the one that we get. And if you draw the trans, you'll get points off. All right. Now, now let's look at when it's on a ring. Okay. When it's on a ring, we have to consider what we call 1,2 transdiaxial. And I'm just going to give the craziest example that I can find, right? So I have the 1,2 transdiaxial that I have to consider. So what that means is that my leaving group that I choose, I have 2 leaving groups here. So this is a very tricky problem, right? 2 leaving groups. I have to choose the leaving group and the hydrogen that gets removed, right? So the hydrogen that's over here, I have a hydrogen over here, right? And I have hydrogens over here. The hydrogen that gets removed and the leaving group both have to be in the axial position. So this has to be axial and this has to be axial for it to be removed, and that's going to determine where I form my double bond, and it's also going to determine in this case which bromine we use. So if we all remember how we do this problem, so I'm going to erase all that. The way that we approach this, I'm going to find the most stable, orientation or chair conformation for this molecule. And that's gonna, orient everything in a certain way. And I'm gonna look at where I have my axial leaving group and an axial hydrogen that's adjacent to it. So the way that we always go about this is I'm going to look at the biggest group on here, which is this group right here, the T-butyl, right? And I'm going to say I want this position to be equatorial. So that means the dark wedge over here is going to be axial, and dark wedge over here is going to be equatorial, and then dark wedge over here is going to be axial. So I found my axial bromine. And so that just means that I'm forming a double bond over here because I have both an axial and an equatorial hydrogen, right? So the axial hydrogen is right here. Does everyone see what I did? So I found the most stable chair, which is making this equatorial, and then labeling everything out and finding my axial bromine that results and my axial hydrogen. All right. So what all this is just I'm going to deprotonate this, and this is gonna form a double bond right there, and this is gonna get kicked off. All right. So I form this CH3 right there. Okay, and I want everyone to know when you form a double bond, you remove stereochemistry. So there's no stereochemistry anymore on this double bond right here. But everything else has retained its stereochemistry. So the Br, okay, and then the T-butyl. All right, so that's our answer. So this would be what our answer is. So you find the positions where you have axial leaving group adjacent to a carbon that has an axial hydrogen, right? And that's really all there is to it. Okay, so these are your SN1, SN2, E1, and E2. All right, not too bad. Just be careful. Just always first thing you do is you look at your nucleophile or look what you have, look at the degree of the carbon the leaving groups are coming off of, and then make a decision. So based on all that information, that will tell you very clearly that whether you have E1, E2, SN1, SN2. And I'm just going to take something from her notes that she has, and I'm just going to put up here, so if you guys want to copy that, she's going to show it, and it's in the notes already, but just for the sake of this video, right, this is a brief overview of everything that we've just talked about, right? So substitution versus elimination. Nucleophile is a weak base, weak base or weak nucleophile, right? So nucleophile, she has these over here. Yeah, so a nucleophile is always a weak base, right? So a nucleophile doesn't abstract protons, it attacks something. So these over here, SN2 it has to be either a methyl, primary, secondary, right? It has to be strong nucleophile but weak base, such as iodide, SH, RS, or CN, and faster rate and aprotic solvents. So that's everything that we've said. And then SN1 and E1 use tertiary, secondary, right? And they use weak nucleophiles, ionizing solvent, aka aprotic, aka protic, right? Protic. And SN1 usually the major product is the major product, it says. And then high temperature increases E1. So there's some extra details that I haven't actually talked about, which is interesting, okay? So SN1 is usually the major product in these cases, but E1 can also form, right? And that's why she has 4 boxes sometimes. But if she doesn't have the 4 boxes, then you're doing the SN1, right? And then you have E2. E2 uses strong bases, so you have OH, OR, NH2, and then you have acetylide. And then bulky bases particularly favor E2. Because that really can't perform SN2. So really, not at all, right? And then the exception is for this is whenever you have a strong unhindered base, right? So an OR that looks like this, right? This will give the SN2 product. So SN2 can work with a strong base only when it's a primary and when it's not bulky, and that'll give you an SN2 product. All right, so that's everything for SN1, SN2, E1, E2, and hopefully you'll be able to do the problems. All right, good luck.